of this amazing school. So today, to start, we have Professor Rodrigo Soto, who is going to give us his last lecture. And I think he will talk about hydrodynamic interactions today. So I hope you enjoy this season. Thank you.
Thank you, Francisca. Yes, indeed, we're going to talk about hydrodynamic interactions and other things, depending on the time and your interest. Okay, so I'll start with Julia's talk, where she presented the hydrodynamic flow generated by point forces in the Stokes regime, in the low Reynolds number regime. And those are her slides that you have the Navier-Stokes equations, but for fluids, but simplified to the case where the Reynolds number is very low. So in that case, the Navier-Stokes equations reduce to the Stokes equations, where you have the gradient of the pressure, the Laplacian of the velocity. Here is mu is the viscosity. I kept the notation mu. Other people use eta. And you have some extra additional forces. And those additional forces are going to be those generated by bacteria, typically. Okay, so, and this equation is complemented by the incompressibility condition of the flow. And if you have a point force like this, acting just on a singular point, then the velocity field takes this form and is proportional to the force because the equation is linear. The Stokes equations are linear. Is proportional to the force. It decays like what 1 over distance. Here you have 2 distance and distance cubed, so it's also 1 over distance, but has a tensorial characteristic. So it's not isotropic. And that defines the G tensor. That this is written in velocity in vector notation. This is written in index notation. So this is the I component of the velocity is proportional to the J component of the force, and there's a tensor that is the Oseen tensor Stokes that has different names. Okay, and then she said that bacteria actually do not exert just a force because they are not supported on a substrate and moving like this, but they are swimming. So if you have your preferred bacteria, for example, your E. coli, and you enclose this swimmer in a volume, there's no external force there, so the net force on the fluid should be 0. And to first order, you say, okay, if there's no net force, you can consider that a bacterium is a force dipole. So the head is pushing the fluid in this direction, and the tail is pushing the fluid in this direction. So you have 2 point forces, and this is what is represented here. So the total velocity field is going to be this. I think that, okay, here she in the plot is just the opposite, is a guy that is doing the force like this, contractile. Okay, so you have that the total velocity field is the velocity field generated by this force, and then you have to consider, and the velocity field on this point depends on this distance R1 and the velocity field, and you have to add the force, the flow generated by this force, and depends on that distance. And far from the swimmer, this is her result, that the velocity field has this shape, and this is what I'm going to discuss a bit more in detail now. So let's do that. What's important is that a bacterium, because I said that the solution for a point force decays as 1 over distance. When you have a dipole, it decays faster because actually there's a first order cancellation on the two forces, and you get something that decays like 1 over distance squares for a bacterium. And this is the flow field for this case, where you're pushing on your head and your tail like this. Okay? So let's do that in a bit with a bit more of detail. So I'm just copying here what was said there, that the velocity field generated by the point force is this G tensor. So it's the velocity field on a position R, and depends on where the point force was acting. And G is this tensor. This is the same thing as before. But when you have a swimmer, I'm going to consider here a pusher. You have the bacterium that is there, and then you say, okay, the head is pushing the flow in this direction, the tail is pushing the fluid in this direction, the bacterium has a size A, so the flow field at a position, and the force, and this is, I'm going to show that this is exact, but you can think that a swimmer is pushing the velocity, the flow like this, and those vectors on these points, this is the distance A, and this is the swimming velocity, the swimming director that we have been discussing for AVPs and whatever. The force, as bacteria are aligned, this force is directed along the director. It's not forming an angle. Okay? So the velocity field is then this sum, is the G tensor, is the flow velocity, is the flow generated by this force. So the force is F times N, but is evaluated at the position R, but it was generated at this position of the bacterium plus 1/2 of body length to the right. So it's 1/2 AN to the right. And you have to sum that over with the flow generated by this force is minus F. But now the flow was generated by a point force here, so it's at the position of the bacterium minus 1/2 body length. So you have this is the flow. It's a complicated expression. So what you do is a Taylor series. If you do a Taylor series for A small, then the first order term cancels, the zero order term cancels, and then you have to take the derivative of the G respect to to the position, and then you have to sum this term, you have a minus, you have here another minus because it's this minus plus this times this plus, you get another minus, and you have to sum the two terms, and you have A, F, NK, NJ. This NK comes from the Taylor series. And of course, you can continue. Okay, so this is the velocity field generated by the bacterium to first order. And, okay,
Can I ask a quick
yes,
question?
Sure.
A technical quick question.
Yeah.
If you go one slide back,
Yeah.
your Green's functions is 1 over 2 pi mu x. What's x there? Is R? Is that R?
Excuse me.
The G,
Yeah.
yeah, this x that's down there.
Yes. Here should be another X. But this X is the absolute.
Oh, okay, that's what you're calling R inside the parentheses. Okay.
Sorry.
Yeah, that.
It was a mistake. X is, yes.
Got it.
Yes.
Yeah.
Okay, so it's the distance. Now it's well written. Okay, so this is exactly what I just have written. And you take all this thing here that is actually a tensor that has 3 indices, IJK. So it's the flow field at the position R, depends on the position of the bacterium, and you define all this thing as Q. I'm using the same letter as before. So Q is AF times A times NN. So this is what is here. Whereas sigma is AF. So AF is the strength of the bacterium. It's like the dipole moment in electromagnetism. It's the distance times the force. So it's almost the same thing as the Q tensor that I defined before, but I prefer to keep the same notation. Yes, but it's a nematic tensor. Okay, so for the flow, it doesn't depend if the swimmer is moving to the right or to the left because it's pushing equally on both directions. So it's this H tensor times this Q tensor. It depends on the bacterium. That is the solution of the Stokes equation, and is the gradient of this G tensor. You have to do some calculations, etc., and you end up with this. It's something that decays like 1 over distance squared. It's okay? No, it's not okay. Yeah? Okay. Okay, so this is the interaction kernel. And, okay. It's not working perfect? No. Okay, I can do it with... Okay, I can do it with that. Okay, so this is the solution. I'm going to work with that and show you how you can compute with that. But before going to this, because I thought that Julia was going to do the multiple expansion, and she didn't, so I'm going to do the multiple expansion. Okay, so I have not that prepared on my slides, but I can do it by hand here. Okay, so what I'm going to do, at first sight, it looks like this is a very crude approximation. Okay, you say, okay, a bacterium is not a point force, and then you say it's a 2-point forces. Okay, okay. You can believe that or not, but probably it's not actually a bacterium. So I'm going to draw a bacterium without flagellum, whatever. Yeah? No flagella. So this is the guy that is generating the motion, and this guy, let's say, that is moving with some speed. Okay? And you want to compute the force on the position R. So what do? You say that each swimmer, bacterium, whatever, on its body surface is producing some forces on the fluid. Because of the flagella, because of everything. Okay? Apparently it's working. Okay, is it working? Okay. So, now you can think that every point of the flagella are generating some forces on the fluid, and the body is also generating some forces. So you have many forces acting on the fluid. You have some force at a position R prime. And then, because the Stokes equations are linear, you can say that the velocity field at a position R now is the integral over the surface of Gij. It's not F. Sorry. Okay, let's call it F. Okay, this is. So you have to sum over all the forces acting on the surface. And you have to integrate over all the whole surface of the body. That's the general flow. So it's much more complicated than that, just saying 2-point forces. Okay, but what would you do? you say that I'm going to look far. So I'm going to say that the bacterium has a center, RB. So I can write it like this. I'm going to write it here. Bi of R is the integral on the surface, Gij R minus RB plus, no, minus plan, okay, everything? Yes. Fj, okay. Yes, simply I add and I subtract the position of the center. I'm going to call this chi. So this is, okay, J R minus RB minus Fj of R prime ds. And now you can say that is, okay, R prime is well defined. Okay. And now what you can do is a Taylor series. A Taylor series in this vector. And why do you do that? Because you're going to look far. So you're going to assume that R minus RB is much larger than T. That's my approximation. I'm going to look far. So this integral of, remember, this is the center of the bacterium. This is this vector that goes from the center to the body surface. So you just have to, you're going to assume that you're far away. Okay, so you do a Taylor series, and this is quite simple. This is Gij R minus, okay, but this, I don't want to write too much. Because when you do the Taylor series, you get that this does not depend on that times Fj minus J. Sorry. It's better like this. Okay, so you do your usual Taylor series. So the first one is you evaluate there, then you derive G with respect to the position, but then you have this psi here, and there's a minus sign because you have this minus sign, then the second order, etc. You continue as far as you want. And it depends, of course, how far you want to see or how close you want to see. If you're going to look closer, then you're going to need more terms, and it's this famous paper that for chlamydomonas you needed up to second order to be more accurate. You needed the quadrupolar term. Okay, but now you look at these things, and you can identify these quantities. I'm going to stay there. So first, the integral of Aj. This is the total force exerted by the bacterium, because you are summing the force exerted by the bacterium at each point and you integrate over the whole surface. And this is 0 if there are no external forces. Yes, this is this thing that Julia discussed in detail. So a swimmer has no external forces, so by second Newton's law, then if there's no net force on the bacterium cannot exert a net force on the fluid. Okay, so that's 0 except for ball box and heavier things that you have a net force. So the next term, I'm going to call it a jk is this integral is a second order tensor. And so you are having this body, and you're integrating this distance and the force that it is here. Yes? This tensor, and now I'm not going to enter into too many details, but it's a 2 by 2, no, it's a second order tensor, and you can write it like symmetric part plus anti-symmetric part. Yes? All matrices, you can write it like this. Okay, the antisymmetric part is associated to what? It means, for example, that has terms like the antisymmetric has terms like this, like A minus A0, for example. Yeah. This means that when you have your body, you have a force like this and a force like this. If you integrate your, because this is, you see, in this case, you're getting a force, and like this, sorry. Yes, everything like this. You're getting, in this case, you can compute it. You have to sum, how is that? In this case, you have positive y. Yes? Okay, you have to. Here, for this point, you have that psi is psi on y, and the force is force on x. Yes? For this point. So in the matrix, this is going to contribute with a term in the, always confused with the orders of the indices, but J is rows, no? Yes, J's are rows and K's are columns, or this is the, okay, so, okay, J is the index of the force, so you have a first row, okay, so you have a positive term here, plus. For this guy here is the same thing, because you have a negative displacement, but a negative force, the product is also going to give you plus in this term. Here, you have that the vector is, the vector is plus on x, but the force is minus on y. Yes? So this is going to, the product is going to give you a negative number. Negative number, but on the second column, first row, like this. Yes? So the antisymmetric part is associated to these kind of things. So the antisymmetric part is associated with torques. Yes, you can easily prove actually that the antisymmetric part of a tensor is the torque. Is 1/2 of the torque, something like this. But it's the torque. But if no external torques, if you are not, for example, some students of us study magnetotactic bacteria, and for the magnetotactic bacteria, there are external torques, because you have a magnetic field that turns the guy. But if you don't have external torques, then the bacterium is not going to act as a reaction on the fluid. So this should be 0. So as a consequence, this term vanishes. You don't have an antisymmetric part, in general. So this AJK turns out to be a symmetric matrix. I'm going to finish here. So Aijk is Aijk symmetric. And you know from linear algebra, freshman physics, you know that from linear algebra that a symmetric and real matrix can be diagonals. So you have two principal axes. And I'm going to call these two principal axes N, not anything, N, and the other one T. So you have N, T, and then this guy can be written like lambda 1 N plus lambda 2 TT. Yes? This is what is written there. Okay, I'm not putting the TT, and this is homework. Yes? You see here that it is lambda 1, that is called sigma 0. And this NN. But there should be another term, lambda 2 TT. Yes? Okay, some homework. Show that lambda 1 that the diagonal part of A does not generate flow. If you put a diagonal matrix there, you're not going to get flow. Because the flow is incompressible. The fluid is incompressible, so you don't generate flows by the diagonal part, and then you can subtract the diagonal. And if you subtract the diagonal, so what we end is something that Aij is Aijk symmetric plus anything on the diagonal. Because the diagonal is not generating anything. It's not generating flow. This is the homework. So you can add anything on your diagonal, whatever you want. What I'm going to add, my election, is not Julia's election, but my election is to take the diagonal, to take it to be minus lambda 2. Yes, this is my election. So at the very end, Aijk turns out to be lambda 1 NN, but lambda 2 TT plus or minus lambda 1 identity. Lambda 2 the identity. Yes? Yes, this is my election. And you learn from quantum mechanics, yes, you have to, that the identity is NN plus TT. Yes? The identity operator is the sum over all brass and cats, or all things like that. Yes? So you end that with lambda 1 minus lambda 2 NN. This is sigma 0. Yes? So some people write it like this, the Q tensor. Julia didn't. She wrote it as a traceless tensor. It's the same thing because the trace, the diagonal, is not generating any flow. Convince yourself. So this picture of a bacterium exerting a force, dipolar force like this, is a picture, but actually is exact. It's exact. It's not that you assume that there are two forces on the head and the tail. It's the dipolar, it's the multipolar approximation that gives you that the total flow is simply this time derivative times that. Of course, there's an error here. Now I realize, but I'm not going to correct it. Oh, I can. Yes. A is defined with a minus sign. Yes? Okay. Yes? This is the way you show that a swimmer can be understood like this. And now if you read this nice paper of Chlamydomonas in the Colson group, what they showed, and they showed that there's a cartoon of the Chlamydomonas like this, and then say that the Chlamydomonas is this. 3 forces. This is twice as large as those other two, such as so it's presented as a dipole and a quadrupole. Well, this is nothing more than going to this next order. Okay? Any questions? Yes.
Hi. So, well, in your diagram, you chose that both forces, well, the force dipole is separated by the whole body length.
Yes.
Is that just something that we decided experimentally? Like you measured, okay, that's the best fit, or you can add it, for example,
Actually, the only thing that you can measure is that. Sigma 0, the total strength of the bacterium. And then you decide that it's a force times a distance.
Yes.
Which distance and which force you take is, you don't care, because the only thing that matters is the product.
Okay, so you can decide that both forces can be inside, actually,
Yes.
the swimmer and all that. Okay.
Actually, it's not, it's the sum of many, many, many forces acting on the surface.
Okay.
Yes?
Thank you.
So typically you say, okay, the distance is going to be the body length, and that gives you an intuition of the strength of the forces. But what's relevant is the total strength, that is sigma 0. Okay, so now we have how's the velocity field produced by a swimmer that is produced by this dipolar tensor. Okay, and in the case like this, and now consider that we have many bacteria. The Stokes equations are linear, so just simply sum up all the contributions. So the velocity field on a position is going to be the sum over all bacteria of the flows generated by all of them. Where Q is the tensor of each bacteria, because each one has its own director. But now things become more interesting for simulations, because if you want to simulate bacteria moving in a fluid, they swim, but they don't know about your reference frame. They just swim on a moving fluid. Yes? So by Galileo, you know that each bacterium is going to swim on the fluid, so they're going to move like this. The position of each bacterium is going to be the self-propulsion times the velocity field at the position of the bacterium. There are some corrections. I'm not going to discuss on the corrections, but there are some corrections here. It's called the Faxen term. But essentially, the guy is moving on a reference frame that is moving already. But the velocity field is given by that. So the velocity of each swimmer is its own velocity plus the sum over all the others and this interaction kernel. H that I just wrote it like this, like a tensor, the position of the guy that I'm interested in, the position of the other bacteria, and their dipoles. Yes. The problem here is that H, as we just saw, decays like 1 over distance squared. So we cannot truncate, as compared with the AVP model that we said, okay, the interactions are short range, and we can truncate the force, and we can use link cells or Verlet list or whatever. Here we cannot truncate. And then the evaluation is n squared. And if you say, okay, I'm just going to consider first neighbors, okay, you're doing something, but you're not doing hydrodynamics. I don't know how to call it, but it's not hydrodynamics. It's something. Yes. If you want to consider hydrodynamics, then you have to consider everybody. Yes? So, okay, is there a solution for that? I know that some people that know the solution, but I'm not going to let them talk.
Yeah.
Okay.
Rodrigo,
Yeah.
I have a question. So until now, you are assuming that your swimmer is swimming in the bulk or like in an infinite fluid. So
Yes.
where the boundary conditions
Appear
enters?
later.
Yes. Okay.
Boundary conditions are going to appear later. Yes. Yes. Okay, so there's a solution, of course. Otherwise, no. Otherwise, no. If there was no solution, you have to live with that. But fortunately for us, okay, so we have not truncate. Okay, sorry. There's something additional that I'm not going to discuss because otherwise the lecture was going to be too long. But if you have a swimmer here, it's generating this flow field that is more or less like this, and it's coming like this. Yes, and it's going out like this. So there's some vorticity. This flow has vorticity. Yes. So now if you put another guy here, this guy is going to rotate due to the other swimmer. So they not only swim on a moving fluid, but they swim on a moving and rotating fluid. Okay, you can compute that. Just give me a minute. You can compute that, and the interaction in this case goes like 1 over distance cube. That is also long range, and you have to also sum all the vorticities around. Yes, please.
I didn't understand the x of rotating that.
I'm plotting here everything in 2D. So the rotation
okay.
is like this.
Okay.
Yes. Because this part is pushed like this, and this part is pulled like this. So there's a vorticity here. Yes. Yes, and there's some interactions, and there's those nice papers, Santillana and Shelley, where they show that pullers have some kind of instabilities and pushers have others, because here you have some rotation in this direction, but if this bacterium were a puller, the rotation was in the opposite direction. And you have some stabilities in one case. Yes. Yes. So very nice interactions in those cases. Okay, so it's very long range. And solutions. Okay, I didn't put the first solution is live with that and write a code, an n squared code. Okay, that's one solution. Another solution is don't consider agents, infinite agents, like many agents, but go to the continuum limit. You can go to the continuum limit and consider that you don't have individual bacteria, but you have an ensemble of bacteria, and you write the hydrodynamic equations for the ensemble, and those were the equations that Julia was discussing a lot, of the equations for Q. Okay. And then the solution is to learn from people of plasma physics that they have to deal with that since the very beginning, because plasmas interact with forces that go like 1 over distance squared. Since the very beginning. Also, people doing gravitation. I don't know, simulating galaxies. They have to live with that. So there's a solution. There are many solutions. I'm going to discuss the particle in cell method because it's nice and you can learn things that can be applied to other contexts. So the particle in cell method is very simple. You simply divide the system in cells and you put your bacteria there. So that's why particle in cell is not very creative as a name. So you have all the swimmers like this. So the velocity field is like this. This is the exact expression. And I'm going to make an approximation. Instead of saying that the position of each swimmer is its real position, I'm going to say that each swimmer is located in a cell, and I'm going to say that instead of being there, is at the center of the cell. So you replace every position of the bacteria, but the position of the cell that they belong to. Being that the case, I can separate this sum on two sums. You sum over all cells, and you sum over all bacteria that are inside the cell. Because everybody in the cell have the same position, that's your approximation, you can take this h out here. And you have h of r minus the position of the center of the cell, plus times the sum of all the q's of the bacteria that are inside the cell. And you call that hat q. So the velocity at a position is going to be the sum over all the cells of h at the position you want to evaluate the velocity minus the position of the center of the cell times the total dipolar tensor of the cell, Q cell. And now for a bacterium, you know that the bacterium was moving like this. And now you make another approximation that is consistent with what you just said. Instead of computing the velocity field at the position of the swimmer, you compute the velocity field at the position of the center of the cell where the bacteria belongs. So you do that. Okay. This is, there's a very nice book. I'm going to give you the reference. I don't remember the name. Is Bini, I think, where they discuss all methods for plasma physics, in particular this one. And this method that I'm just describing here is the one that is in chapter 1. Then you have everything, the rest of the book. Yes? And the rest of the book is that you can do better than this. You can do now a multiple expansion, again, on this H. Here you say that's on the center of the cell plus a correction because bacteria are not exactly at the center, and you go to next orders. You can do that. The same here. Okay, but then this is the velocity of the swimmer. So the algorithm is very simple in principle. For each cell, you have to compute the Q, the total Q on the cell. Then the velocity on each cell is the sum over all the other cells, H times Q. And then the velocity of a swimmer is its own velocity plus the velocity of the flow in the cell where it lives. So the algorithm is like this. Then you run your loop on time. For all cells, first you say that the total hat Q is 0. That's okay. Here the drawing is not correct. Okay, so that goes you a total time that is on the order of the total number of cells, of course. Then for all particles, you compute. You see on which cell the cell lives. This is this function. Given the position of the swimmer, you compute the cell, and you add to that cell the strength of the dipole moment of the bacteria. Yes?
Quick question. You keep track of the real positions of the particles, right?
Yes, you have an array
they're
of the
going to be
real
updated.
positions.
It's just the equations that get simplified with putting them in the center of the cell.
No, yes, that is, the position is a real position that is moving smoothly. There's the velocity field that I'm evaluated at the cell where it lives.
Yeah.
Yes. So here I have to see in which cell it belongs. Then I add the Q tensor. And now you have this computation of this part For all the cells, you run over all the neighbors, or no, not neighbors, all the other cells, and you sum the velocity as h times hat q. Okay. This is written easily because actually this is a tensor, this is a tensor, you have to sum over all the indices. Okay, like in general relativity. Okay. And then finally you run over all the particles. Again, you see in which cell the bacterium belongs, and you simply say that the position is going to be this previous position times its own velocity, the velocity at the cell times dt. That's it. That's the algorithm. This term is, this part is order C, is the number of cells. This part is order of the number of particles. This part is order C squared, it's still C squared. But you have much less cells than particles. So it's much faster than order n squared. And then you have to move all the particles. So this is the crude method that we're going to use with boundaries. I'm going to come back to that again. Yes? But still, normally you want many cells, and it's going to be slow anyway. Not as slow as before, but slow. So, but anyway, but you can do better than this. Because the velocity on each cell is the sum over all other cells, h times q. So this is a convolution. And if you have periodic boundary conditions, I didn't put it there, but if you have periodic boundary conditions, and this is an important issue, you can use Fourier transform, because in Fourier space, a convolution is simply a product. So what do you do? First, you have to compute the Fourier transform of H. You have to do it once, with any precision as you want. Then the computation is like this. At each time step, you compute Q at each cell. Okay, that was easy. Then you Fourier transform. You get the Fourier transform of Q. Then in Fourier space, you simply multiply the two things here. And you get the Fourier transform of the velocity. And then you compute the inverse Fourier transform, and you get the velocity, and then you move the particles. The advantage of that, okay, you have to compute Fourier transforms, so that's an overhead over your code, but the Fourier transform computation is very fast, is C log C. So the whole code is order n plus order C. It's very fast. That's what people in astrophysics or in plasma physics do. Yes? With Coulomb interaction, the Coulomb kernel instead of the Stokes kernel. Plasma physics is much easier because the Coulomb kernel, because charges in plasmas are scalars. It's a charge, 1 Coulomb. Our charges are forces, so it's a vector. So we have one index more. Okay. You have to, okay, you can live with that. But this is the way that you compute you can simulate many particles interacting with hydrodynamic forces.
Can I ask something?
Yes.
That's kind of general. It's valid for this method, for instance, and also for other methods that you mentioned, for instance, when you keep track of a neighborhood of particles.
Yeah.
How do you, is there a systematic way of controlling the error that you're controlling the error?
The error of your approximation.
Of your approximation, yeah.
Yes, I think that there are systematic ways to estimate your error. Not necessarily controlling, but estimating giving a bound of the error. Yes.
Okay.
Like in, and this is, I think, very well discussed on this book. That I think it's called simulation using particles, something like this. It's a very general name, but it's actually just plasma physics.
Okay.
Yes.
Okay.
Yes, but you can, of course, the smaller the cells, the better.
Yeah, I understand. You can play with it, so that
Yes.
it's better. But how do you control it on the fly, like
No, it's not on the fly. You have to
you
test.
have to do a simulation.
Yeah, you have to run some tests and see that the structures that you're creating, for example, Julia showed us some nice instabilities that developed.
Yeah.
So you have to, your cells should be smaller than the wavelength of those instabilities.
Okay.
So you first look the instabilities, okay, say maybe I'm too coarse, I have to refine the grid, etc.
Okay. Okay.
Yes.
Yeah. Thanks.
Okay. Boundaries. I'm going to be very short on this, but what do you do when you have boundaries? So in a solid boundary, there are other kind of boundaries. We were seeing yesterday, yes? This boundary that is not really a solid boundary, but a membrane, a capsule. Okay, this is another kind of boundary. Or you can have fluid interfaces, fluid air interfaces, other kind of boundaries. Just solid boundaries just to be concrete and to finish today. Okay, so the velocity field on the solid boundary must vanish. It's called a non-slip boundary condition. And for that case, you can compute the new Green function, in principle. When you have solid boundaries, you can compute the Green function. The Green function is, I'm going to go very fast back, so don't get sick. If you have too many caipirinhas, maybe this is going to make you bad. Okay. The Green function is the solution of this equation, putting a point force, but now considering all the boundary conditions. In principle, you can do that for some cases. There are some explicit solutions for some cases. There are some numerical or tabulated solutions for other cases. So you can compute the Green function, and then, boom, 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 boom. And then the velocity field is going to be the Green function times the force. And the Green function is good. That is, if you evaluate on the border, it's going to be 0 no matter where you put the source. All sources are going to produce a 0 velocity on the border. There are two problems. The first one is that this Green function is only known in very few cases. The simplest expression is for a flat surface. It's called the Blake solution. It's already ugly. It's known also for a sphere. It's even uglier. For two parallel surfaces, it's also known, but it's a series of many terms. But you can keep some of those terms, and it's OK. But there's another problem, and you can do that. The other problem is that because you have a surface, now you don't have space translational invariance. So the Green function, maybe you noticed I put a comma here. I didn't put a minus sign. It depends on both positions. Yes? So you cannot use the Fourier transform trick in this case, because it's not a spatial invariant. It's a translational invariant. Sorry. OK, you can live with that, and you have to use this method. No Fourier transform, but you can do it anyway. There is a solution, nevertheless. You can anyway use Fourier transforms, but you have to do other things, and here is where I'm going to stop for this part, are what they call immerse boundary methods in general. I put methods because there are some things called inverse boundary method, immerse boundary element. Okay, I'm not going to enter into too many details, but the idea is that you can replace the surface, but a set of forces sitting on the surface. Okay, because what's going on actually? When you have a swimmer, okay, here, when you have a swimmer that is generating some flow, and you have a surface, the flow the fluid wants to enter into the surface, is exerting some pressure on the surface, but the surface is not moving. Why it's not moving? Because the surface is generating a force against that. So the surface is reacting to the action of this bacterium, not to move. Yes? So it's generating. So actually, this is real. A surface is reacting by a set of forces. So you say, okay, my surface is going to be replaced by a set of points, each one exerting some force on the fluid. The problem is that you don't know the forces. Okay, live with that at the moment. But those are forces. So the total velocity is going to be the sum of all bacteria of this H tensor, that is the dipolar approximation, this thing there, the gradient there, times the Q tensors of the swimmers, plus, because those are point forces, the G tensor times F of all the P's on the border. You have to. How do you obtain those P, those forces? Those forces are such that if you evaluate the velocity on the position of on the surface, that should be 0. So you have that. If you evaluate the velocity at a position Q, you get HRQ minus RN, QN, GRQ minus RP, FP should be 0 for all Q's in the border. So it's very complicated, looks very complicated, but at the end it's a matrix QP. Oh, yes, QP acting on FP, so it's A times F. And this guy, you take it to the right, is a right-hand side. So it's a linear problem. So you just have to solve a linear equation. High school physics. Yes? The only problem is that you have many, I don't know, 1,000 points. So it's a 1,000 by 1,000 matrix. Okay, well, you can live with that. Computers can live with that, not you, computers. But it's a linear problem. The difficulty here is that A is very dense as a matrix. Why is very dense? Because A is this G. G decays very slowly, like 1 over distance. Yes?
Sorry?
Yeah.
But then the forces are calculated for each cell. You are still keeping the cell...
I'm not using cells yet.
Okay, but then this force should be a continuous distribution.
Yes, but you don't put a continuous distribution. You just put many.
Okay.
As many as you want to cover the surface. Yes. So, yes. Okay, I was saying that this G decays very slowly, like 1 over distance. So every point interacts with every point. So the matrix is very dense. So this is a heavy problem in linear algebra. Yes, it goes like n cubed in the number of points. So it's very expensive. But what are you going to do? You're going to compute the forces, those forces. With that, you compute the velocity field using, for example, cells. With that, you're going to move your bacteria. Now you have to compute again, because you move the bacteria, so the bacteria change positions, the Q tensors also change, so you have to get the new piece, the new F, at each time step. But as bacteria move little between one step and the next one, you expect that the forces are going to be similar between one step and the other, and the next one. So instead of putting MP inag solve of the linear problem, you use an iterative method. You use an iterative method to solve this equation using the previous step as an initial condition. And you have to iterate, I don't know, a few times, and you get the solution. Okay. So this is the method. It's heavy, but it can be done.
Is this similar to the stochastic dynamics, or is different?
No, stochastic dynamics is completely different. Stochastic dynamics is a method developed by John Brady and Bossis? Yes?
Howard Stone?
I don't know. Well,
I think
okay.
so, yeah.
But if you want to simulate colloids or bacteria or whatever, but with a lot of detail on the nearby interactions, when the colloids are very dense. And it's not useful here because we already started using a multipolar expansion.
Okay.
So, no. Okay, so with that, I'm going to finish with hydrodynamics. Let me see. Yeah. What's that? Ah, this is the book. Yes, I'm going to share it now. Si quieres me manda un WhatsApp, me lo mandas por WhatsApp. Okay. Okay. Any question here? No? Yes? No? Yes? Okay. So now I'm going to finish. I have 20 minutes, 10, 15 minutes, something like this. Yes?
Yes.
Yes. Okay. So I want to finish with something that is not active matter really, but it's something that is useful for many things and soft matter and simulations. Yeah? That is response functions. And there's nothing next. Oh, sorry. It's nothing really. Yes? I didn't have time to prepare that on the slides, but I have the blackboard. Yeah? So I want to discuss a bit on response functions and something that I think is very important. Maybe you're not going to think that, but I think it's very important because there's the source of, I don't know, some errors or some misunderstandings on what you're doing. So normally, we use simulations to get some results, and some typical results that you want to get are response functions. For example, what happens, for example, with a bacterial suspension if you shear it? Or if you put an obstacle and you drag the obstacle, for example, I think that, no, Julia didn't discuss on that, but for example, there are some nice results on putting things inside tissues and pulling this thing, and you see the viscous, the drag force on this thing. This is a typical response problem, that you have your systems, you perturb it, and you want to see how it responds. So just to take you back to the things that you know more, I'm going to start with the electrical conductivity problem. So the electrical conductivity problem is that you have a material. I'm going to be classical to my thinking, but it's the same thing. You have some electrons here. You apply an electric field. You know, history made us to have to think in the opposite way. Electric field should be to the left to get a current to the right. Yes? No, the current, no, okay. That's the opposite. The electrons are going to move like this. Okay. So and the current is going to be like this. Yes? This is the classical electrical conductivity problem. Yes? So now I have my notes here. So I said, I have the notes, but not beautiful notes. So you expect that if E is 0, then G is 0. Yes? It's not a superconductor. And then the question that you want to answer is, how is G as a function of A? And ohms tell us that J is sigma E. Yes? This is the electrical conductivity. When you were first taught on that, you say, okay, that's life, or I don't know, I believe that, whatever. But now that you're older, then you know that this looks, when you look at this, that looks like a Taylor series. Yes? You know that it's the first order term of Taylor. And life, real life, should be like this, sigma 1 E plus sigma 2 E squared plus blah, 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 blah. Yes? It looks like if 0 at 0 and then a linear term, you say, okay, it's a linear expansion, Taylor expansion. Why do we always state at linear term? Do you know why? It's not because it's not for simplicity. Hmm? It helps? Yes. But why do we stop there? Why there are not so many books on non-linear electrical conductivity? No? The answer is that the electric field is really small. What's the magnitude of the electric field? Okay, this question does not make any sense because it's a dimensional quantity, so you have to make it dimensionless. So, field you have to make something dimensionless out of the electric field. Yes? And, okay, now, before going to that, the typical dimension field, electric field, is on the order of 220 volts divided by 1 millimeter. This is the typical electric field that you have in everything that you use. Yes? So you have to make a dimensionless electric field. With what you compare is the electric field with a charge. This is the force. A travel distance that gives you an energy, and you have to compare to the typical energy. So this is the work done by the electric field, and you have to compare with the typical energy. What's the typical energy? 1 electron volt. Now, if you put the numbers, this is really, 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 really small. For all practical cases, the electric field is extremely small. Yes? Because you have to compare with 1 electron volt, that is a huge energy, compared to L. What's the typical L? L, 1 angstrom. Is the hopping distance for the electron to change from one equilibrium position to the next equilibrium position. I know I'm thinking classically, but okay, it's one classic equilibrium position to the next equilibrium position. So that's a very small quantity for the electric field. Yeah? That's why you stop at the linear term. Yes? Second example. Shear flow. So you have here a fluid, and you move the top surface with a velocity. And that bottom surface is at rest. Just shear your flow. And you know that it's going to create something like this, a velocity field like this. Yes? And Newton made many things, and among other things, he made that, said that the force on the top surface, the force on the surface, is the viscosity, the area, and the velocity divided by L, the gradient. This is viscous law, Newton's law. Yeah? So the larger the surfaces, the bigger the force, of course. If the velocity is larger, okay. Again, when you look at that, it looks like a Taylor series. Yeah. So what's the next order? So we have to make B, for example, can be or the order of 1 meter per second, but you can do it bigger, larger, yeah? You can go, I don't know, 1,000 meters per second. You can do it. I don't know. It's quite easy. Well, it's not that easy, but you have to take a plane, and you have that. Yes? The boundary layer is on that order for a plane. So how do you make a dimensionless velocity? You have to compare the velocity with another one. Yes? So the first thing that you can come out is you can compare with the sound velocity. Yes? You say, okay, compare with the sound velocity. Or that is, you know that is the same thing as the thermal velocity, the Maxwellian thermal velocity. Yeah? And then it turns out that it's not so small. Okay, in this case it's small. In this case it's not as small at all. But nevertheless, planes are computed when they do the simulations using Navier-Stokes equation using this law. Why? So here you can think that maybe I have to go to nonlinear order. The problem is that this is not the good scaling. This is not the good comparison. And this is not a good comparison because of Galileo. Galileo told us that it's not relevant the velocity that you're moving. The only things that matters are the relative velocities. Yes? You need relative velocities. So the way to make something dimensionless is to build a dimensionless velocity, a relative velocity. I have to compare 2 points. Yes? Because the fluid is made of molecules, the difference, so now you have to compare the difference, now compare with the sound velocity. But because the fluid is made of molecules, the difference velocity is the gradient, B divided by L, times 1 angstrom. This is the relative velocity that matters, the relative velocity between one atom and the other one. And now you compare with the sound velocity. And this turns out to be also very, very small. Because you make gradients. Here I'm making a gradient of 1 millimeter, 1 meter. You can make a 1 millimeter. You can do active matter, and you're making gradients on the order of 1 micron. 1 micron anyway is much larger than 1 angstrom. So this scales like 1 angstrom divided by L. So unless you're using L's of the order of 1 nanometer, your velocity gradients are always small, in reality. Okay, so what friction drag I'm not going to tell, because it's the same thing, but okay. Why I'm discussing this in the context of active matter or in the context of simulations? Because what do you do now? Shear flow in computers. You do the same thing, like this. You put the walls, you put atoms, and now molecular dynamics. You put atoms, and you shear. Yeah? Now, depending on your money, this length can be, I don't know, 100 atoms. But this is when you have a lot of money. Typically, it's going to be 20 atoms, or even less. Because you're making a simulation, you're putting a million particles in 3D is making a box of 10 by 10 by 10 angstroms. So in simulations, gradients of velocity are huge. Not only because you take your system small, are huge by 2 reasons. Okay, that's okay. An analytic continuation of the okay. The gradients are huge because your system is small. First thing, you're just using 10 angstroms on your box size. but also because you put typically V large to improve. I'm going to put that in quotes, noise, no, signal to noise. You want to improve signal to noise ratio, because if you do a simulation with a small velocity gradient, you have so many fluctuations on the velocity in the system because you have particles moving there, that you see a signal for the force, but the force is going to be weak. So it's going to fluctuate a lot around 0. And then if you take the average, you're going to notice that it's different from 0. But it's difficult to get that average. So you say, okay, I put larger velocities to improve the signal-to-noise ratio. But you're putting large velocities in small systems, then you get nonlinear responses. So this is my warning. Always check that you are in the linear regime. So you get nonlinear. So you have normally to take you have to make several simulations on the force as a function of velocity, and then extrapolate to 0. And here is the viscosity. Typically, the viscosity is not in your simulation regime. The viscosity is beyond the simulation regime, but okay, you can get it if you properly extrapolate to 0. You're getting nonlinear response. This is the first thing, and the second problem that, okay, I have not thought on active matter for the second problem, yes? But the second problem, for example, in shear flows, is what is called secular effects. Is that you know that shear flows produce heat, yes? And you do something like this. Shear flows produce heat, but the heat goes like the gradient squared. Yes? So normally, in real life, shear flows do not hit your experiment. Not really, not too much. This quantity is very small, so typically you're not hitting too much your experiment. In simulations, as your gradient is very large, you are hitting your experiment. And if you do simulations like this, you start at one temperature, and you end at a very different temperature. So your system is not steady. And then you have to put tricks, depending on the context, to cut those secular effects that are not supposed to be there in the linear response. I don't have an example for active matter, but you can think of what you're doing and check that you're really, if you're comparing with theory or you're going to give a transport coefficient, typically a linear transport coefficient, check that you're in the linear regime and that you're not hitting or producing some nonlinear effects, some secular effects, as I was discussing. Yes? Okay, so with that, I'm done. It's time to coffee. Yes, for everybody. Okay, thank you.
Thank you, Rodrigo, for this amazing talk. So now I'm concerned about my shear flows and divertidos. My first papers. So somebody has a question? Yeah.
So here when you talk about F, which would be the viscosity, you are thinking of the sheet of air that's close to the surface. I'm thinking of a car, for example. You change the regime when you go from a laminar flow at low speed, and then you go to high speed, for example. Then the global force you feel will be different, I believe, and it's not, and it will be related to the velocity.
Yes. Okay. So okay, I have to discuss this because otherwise there's a confusion. That is, this Newton law is valid for all flows that you know, even those very turbulent flows where you know that in a car, I'm going to make a children design of car. Okay, even for a car, with a car, you know that the force goes like velocity squared. This is the drag of a... But this is the average force and the average speed. But this force that goes like v squared actually is the sum of many of those that are really linear on the local gradient. The problem is that the local gradients in a car can be, I don't know, in the scale of 1 millimeter. I don't know what's the Kolmogorov scale for a car, but can be very small, the vortices. And so in a car, this L depends on V. And that's why it becomes V squared. But the Newton's law is still valid if you are able to measure very, very close to the car surface. Is going to follow this law.
So, if you have an active particle moving in a fluid, or a set of active particles in a fluid, you can call them swimmers or not, depending on whether hydrodynamic interactions are important.
Yes, wet or dry active matter.
Yeah.
Yes.
So, what are the parameters and how to estimate whether hydrodynamic interactions will be important?
Ah, okay. Maybe Francesco is going to tell us about something like this. But okay, you have to estimate first. You can estimate the effects. That is, for example, you have some velocities, induced velocities. How's the importance of those induced velocities on the thing that you're measuring? If you're considering long-range effects, hydrodynamics has an effect there. Has an influence on the long-range effects. So you have to think on that if what you're observing depends on the extension, for example, of those vortices, etc. But also you have to think if you have surfaces or not. Yes? If you are crawling, that is, if you have bacteria close to a surface, for example, in that case, the surface is exerting a force on the fluid, but you can think as a sink of momentum. And the green tensor, instead of decaying like 1/distance, I don't remember, I'm not going to lie, but it decays faster, close to a surface. So you don't have too much of long-range interactions if you're moving in a surface, close to a surface.
But
yeah, sorry, just to finish. And if you have two surfaces, okay, it's even worse. It's even faster. Yeah.
But for some fluids, this is, depending on the viscosity, this might be not relevant.
Yeah.
Or is this always relevant?
The viscosity factors out.
Okay.
Yes.
So this is relevant regardless of the fluid.
Yes, I would say that. Okay, Aparna, and then you. Yeah. No, the viscosity scales out.
So that's basically what I was going to say. If you're actually looking at data or you're deciding what simulation you want to run for a particular system, it's best to go back to colloidal literature and ask what is the lubrication length scale for an object of that size and what is the density of objects that I have and what is the scale of my system. Colloids people who do dense suspensions know when hydrodynamics is important and when it's not, right? So you use that and then scale it up to the active flow. And that gives a very good ballpark estimate of when the hydrodynamics is going to be the most important thing to care about and when you don't care about it and you can just get away with some local interactions or modified local interactions.
Yes. But yes, it has been a subject of debate of how important are hydrodynamic interactions. Yes.
Hi, Soto. I'm not sure if I understand what could be secular effects in the shear flow simulation. Because, for example, if I have a PDE that is simulating the density, and I have an external field coupled to the density, I could generate shear flows And I'm not sure if I know how to identify a secular effect in this case.
A secular effect is that you're supposed to be in a stationary state, but you observe your system is actually not steady. It's heating or is being modified by some accumulated effect. Yes? Because in shear flows, normally, if you shear, you can do the experiment of, I don't know, rheometers, when people do rheometry, I don't know, they can run it for quite a long time, and it's okay. Quite long time on the microscopic scale. That is, you can run it for 1 million picoseconds, and it's okay. Yes? I'm not running the rheometer for 1 hour. Of course, it's going to hit, but 1 hour is millions of picoseconds. It's too much. But picosecond is the scale, typical scale of molecules to collide. So you can run your rheometer for 1 million picoseconds, and it's not going to be heated. If you do that in a simulation for 1 million picoseconds, it's going to be a very, very different temperature from the initial state. Yes.
Okay.
Now, in active matter, just to finish, you can think on taking your thing and pulling an obstacle here, an object here, like this. When you do the experiment, you're going to pull it, I don't know, 1 millimeter per second, something like this, probably slower than this. But in simulations, maybe you can do it much faster, and you're going to create, I don't know, waves or things that are, maybe you're not letting the system to reaccommodate after you're pulling. So you have to be, okay.
Yeah, I have yeah, Emmanuel.
Thank you, Rodrigo, for the lecture. Actually, I have a curiosity. If we put active particle in hydrodynamic medium, for example, did we find still motility-induced phase separation too in this kind of medium?
MIPS with hydrodynamic interactions.
Yes, I think
Yes.
Andreas Soto.
Okay. Okay, you know much better than me the literature. Yes. Okay, it has been seen.
So I have a question with the boundary immerse
Yeah.
methods. So in that case, if you are close to a non-boundary, non-sleep boundary, your tensor is the Blake tensor, and then you have images.
Yes.
So my question is, if you have to do the same thing with the forces on the images, or you just move the real bacteria and then you relocate your images below?
No, with the immersed boundary method, you don't have images.
Okay, that's where, yeah.
No, you don't have images at all. You have, okay.
So you skip the images and you have just your real bacteria, which is relocated because it's already following the non-boundary.
Yes.
Okay.
Yes. Yeah. Maybe. Okay, I'm going to rewrite my slides, but okay. Electromagnetism. If you have a conductor here and you have a charge here, you learn that this is equivalent to having this, yes? Q and minus Q. Yes? Minus Q? For the, yes, okay, for the conductor, because the insulator is gaseous. Okay. This is the image method. But what happens in reality? In reality, you have the charge, and here you create a density charge that actually is negative. Yes? The conductor attracts. So this is actually the immersed boundary method. You're putting, actually this is the reality. You have several forces acting on the boundary.
Okay, great.
Several charges. Yes, that's the same thing.
Okay, okay, great. So let's thanks Rodrigo again. Thank you for this amazing course. I have learned a lot, and I hope that everybody enjoyed that.